See the rec? The numbers going up? Okay. Yeah. Alright. Okay, everyone, so I'm going to try and jump in as well and give you my idea for how I think we'll get to Alpha Centauri. So we've gone over the basic stats. It's 4.3 light years away. There are 2 stars there. We think we'll probably have Earth-like worlds. A little hard to figure out what's actually there right now because of the fact they orbit each other. But, you know, well, here's how that works, right? When they get close to each other, you don't know what you're looking at, and they basically blur each other out. So the European Space Agency and the Planetary Society are in a competition where every time that window opens up again for a few years, they take the new instruments out and they take readings and they try and see if there are planets there. And at the last round, a couple of years ago, the European Space Agency said they found a planet. And then other scientists who may or may not have something to do with the Planetary Society went, oh, well, maybe you've over-extrapolated your data. And now everyone's frantically building new instruments and testing new equipment. So when the planets, when the stars again open up again, they can take a look and get more readings. So it's an exciting time for planet science. So we talked about the missions here. The flyby, you go right in, you go right out. The probe, you drop landers, you drop rovers, you go into orbit and you study things for a while. The manned mission, you send explorers and then colonists. Now, the only way that we can have people running off to Alpha Centauri by 2100 is if you have a space race. And the space race has to be something people are really going to get behind, or something people would care about. Right? So I think we'll see a space race start possibly as early as 2018. 2018 is when the James Webb telescope is going up. That's going to be the successor to the Hubble telescope. A whole bunch of telescopes, like really big science telescopes, were thought up around Hubble and around the Galileo period. And the James Webb is going to focus more on infrared, so look at gas clouds, it'll look at worlds, and just work out what's going on over there. And it has a much larger area than the Hubble telescope. And what that means is we're going to be able to see not only Earth-sized planets around, well, whatever star is looking at, but you can also see their color. And color is very important because then you can tell what's in the atmosphere. Right? And that's key because we're going to find oxygen maybe. If we see oxygen, lots of free oxygen, it's a very, very clear sign you have life that is Earth-like on that planet. Because oxygen is a very reactive gas. You don't find it in the atmosphere anywhere in our solar system. Because it just reacts. Mars is red because it's covered in rust. All the O2 is gone. All the free oxygen. So if we have lots of free oxygen, like we have 20% of our atmosphere is free oxygen. If you have something like that happening, it's because you have a titanic process replenishing that oxygen. Right? That's going to be life. So with James Webb, we'll be able to spot things like that. So hopefully with James Webb, we'll find there are worlds that are in Alpha Centauri, and we'll find oxygen. Right? And that's going to be grounds for a space race because someone's going to put people there first. Right? And I think that the race will be between America and China. We already see China gearing up for a race. So, but not for Alpha Centauri, that's for Mars. We'll get to that. Really quickly, this whole thing where you look at the light coming from a star or an object to figure out what it's made of is like it's old science. It goes back almost 100 years. There's an IO9 article about James Webb Telescope, and you can tell from the way it's written that they just figured this out maybe in September, which when the article was written. So I'm not fond of Google writers. Anyway, so we talked about the fuel problem. The more fuel you carry, the more fuel you need to carry. And what this finally comes out, we saw in Hasitha's presentation, the idea is to collect the fuel as you go. You simply don't bother to carry fuel. Okay? I've taken a more traditional route. You're going to carry the fuel. So if you're going to carry the fuel, you need to get the most thrust out of each pound of fuel you have. Right? And when we're at these levels where we're basically going, well, you know, forget about what happens if you burn your fuel to get energy. What if you annihilate your fuel? What if you break the atoms to get the energy out of it? Because that's the level you want to get to. Right? And the most energetic processes we know, or what we use today for doing that, are nuclear fission and nuclear fusion. Fission is atom bombs, right? The Hiroshima and so on, right? Fission will release 0.1% of the energy in a nuclear atom. 0.1%. So not 1%, or 10%, right? Fusion's a little better. You get 0.7 off 8% of the energy. And fusion powers the sun. And so you're not getting great efficiencies with nuclear fission or fusion. Okay. So let's take a look over here. Hasitha talked about the Daedalus project, and again, the Icarus is now working. The Icarus project is like what they're doing with that now. The British Empire Society. Daedalus, I'm sorry, Daedalus is a mess. It came out of it's what people thought, right? They came out in the decade after they went to the moon, and think of the excitement people had that we went to the moon. It was an amazing ride. We could do anything. There was nothing we couldn't do. We were going to go to Mars, you know. We were going to 2001. We already have a lunar colony in 2001 ready to go when they sent off Dave Bowman and gang on a 4-year mission, which in the book is actually Saturn, right? So people thought that big money was always going to be a big thing in space science. Nothing was too ridiculous. You could try it. So with Daedalus, you want to have 54,000 tons of fuel to move a 500-ton payload. Right? Today, not only is a 54,000 tons of fuel a ridiculous idea, even the 500 tons of payload is kind of ridiculous. And that's a huge payload, right? And here's what makes it worse. For a system like this, they are planning to use something called helium-3. It's a heavier isotope of helium. It has an extra neutron. It fuses these and gives energy more readily. If we want that kind of helium-3, we're going to have to go to Jupiter to mine it. And then we'll die and go, I'm glad I went to Neptune instead and mined it. Right? So we've got to do incredible projects just to get the fuel to launch an incredible project like this. Right? And it's not going to, Daedalus is going to fly by. What's the point? You just go in and you get out. So there's a solution to this. Before we get to it, I want to talk about this man, Robert Forward. He was a physicist. He died relatively recently of cancer, unfortunately. He worked for NASA. He worked for the United States Air Force, doing a lot of projects. He was really big into space science. Right? He wrote a lot of science fiction. All of it is terrible, right? But he knew his stuff. And like every now and then in a field, you get someone who stands out. And when he walks and opens his mouth, everyone shuts the fuck up and listens, right? We have that now in transhumanism. There's a guy named Andrew Sandberg who took a brief interest in it and then disappeared for a while. Robert Forward was the same thing for interstellar propulsion. He designed systems for sending light sails toward the stars, wave riders and beam riders, and he talked about antimatter. I think it was the idea he was most into in the end was antimatter. In fact, I have his book here on the top, which is very, very hard to find now. But we'll get to that. Anyway, so he said the way to do it was antimatter. Let's talk about that. Now, when we think of antimatter, who can tell me what kind of efficiency you get when you have antimatter collisions? I want a percentage. Who can give me a percentage for antimatter collision?
100%?
100%. Most people in the antimatter collision, they think 100% energy conversion, right? This is not actually true in all cases. That's specifically what happens when an electron and its antimatter equivalent, a positron, collide. You get 100% energy. And you get it in the form of really high energy gamma rays, which is nasty shit. You don't want to work with that. It's almost impossible to deflect and bend. It's just nasty, right? And you don't get much propulsion out of that. So I'm not going to get into the details of that because that is heavy science, and I'll happily talk to you about it at the end of the presentation. What I want to talk about instead is proton antiproton annihilation. Right? When we think of protons, we think of a little particle going around, but you add an electron to that, we have hydrogen. So protons are plentiful. We can get protons pretty easily. We'll get to how you get the antiproton. That's kind of a big deal and a big problem with this presentation. But with the system here we're looking at here, which uses protons, antiprotons, is called a beam core system. What happens is you collide a proton and antiproton, and you have a chamber which is basically a magnetic field. This core. And what happens there is that things that have no charge just go right out, right? The gamma rays, you do get some gamma rays, those go right out. And you've got to shield yourself so you don't get irradiated by them, right? But the magnetic field holds the charged particles in and bows them out. Bows them out the back. And then they in turn decay and break up. But they're moving so fast that time slows down for those particles. So your ship has moved away before they break up. Right? So using relativity in your engine. Right? So the efficiency in a beam core system is not 100%. It's anywhere between 30 and 50% depending on how you set it up and what you're doing. Right? So 30 to 50% is a hell of a lot better than 1/10%. Right? It's still not great, but it's a lot better. And this wouldn't just be a system that used antimatter out the engine. You'd need a propellant anyway, right? Because you're still not getting great thrust if you're just using a really energetic system, which is a whole ton of energy. You want to have that perhaps excites the propellant set it out, right? And you could use anything for this propellant. You could use water. It should just be used water. You know, it's light, it's got hydrogen in it. It's easy to store. It doesn't kill you if it gets loose. Well, that's pretty harmless stuff. So you can use water in this. And Ford has done some math for this. A 1-ton vessel would need 18 kilograms of antimatter to do a flyby. That's it. Yeah? If you want it to slow down, you need 350 kilograms, and now you go into orbit. There's your probe. 350 kilograms of antimatter, you can go into orbit. And that works for all the mission profiles. You can use antimatter. It works across that range we saw, from flyby to probe to explorers to colonists. You can use antimatter. It is ridiculous to get up and say that we should go out and put out hundreds and hundreds of kilograms of antimatter per project, right? Because this is some seriously elusive stuff, right? It's not that easy. First off, how do you store antimatter? If it comes into contact with anything, if it comes into contact with hydrogen, right? If you leave antimatter out in space, it will eventually bang into hydrogen, and then it will explode. Right? It's some nasty stuff. It's ridiculously dangerous. We can use magnets to contain antimatter. That's how we do it now. Those magnets will be big and heavy, and they can never fail. So if they do, your ship will explode. Your factory will explode. Your country will explode. Right? That stuff is pretty volatile. So there's a challenge there with storage. Right? The storage problem is nothing compared to the manufacturing problem. Right? We produce antimatter when we accelerate particles and smash them into something. Right? That's how we make lots of interesting particles. And antimatter produces a byproduct. Right? CERN in Europe, that produces antimatter, and in 1 billion years, it'll have finished producing 1 gram. Okay, so it's not particularly useful. You can find it in nature. It's a little hard to get. It involves space missions as well. I don't want to get into it because it's a little too complicated, I think. It is very hard to find documentation on how to make antimatter in mass. There are all kinds of things. Robert Ford had this ridiculous thing we talked about, putting up huge solar panel stations all over space to get the energy to make antimatter. And none of these things are even vaguely remotely practical. There's one thing which he talks about. It's in this book. There's one thing he spends a few throwaway lines mentioning, where he says you could take a 100-meter track. Again, you heard Hasitha talk about accelerators, the cyclotron, where you spin it round, faster, faster. Have a straight linear track for 100 meters. You take heavy ions, like uranium or thorium, something radioactive probably, right? And you smash it, you shred it to bits, and that will produce antimatter. And he reckoned, and didn't go into any details, and there's a reason for that. I think nobody wants to talk about this out loud, and I'm sure people are working on antimatter, and they're not really being too loud about that. But he reckons that you could produce up to 1 gram a day in a system like that. 1 gram a day, and there's almost nothing about it there. You're looking. Right? So, and by the way, this book you cannot, it's a reprint. There's no EPUB of this, there's no electronic version. It's out of print. It's hard to find this information. Right? So I'm saying, okay, fine, let's work with that system where you can produce 1 gram a day with a linear accelerator where you're shredding hydrogen, you're shredding uranium. Right? I don't know what the actual term for that is. I don't think there is an actual term. I'm calling it uranium shredding. Right? Does that sound like a safe thing to do?
No.
Probably not. Like you're basically taking extremely valuable heavy metal ions and you're just making waste. You're making nuclear waste, tons of nuclear waste, making it as fast as you can accelerate it. So you've got all kinds of problems right there. Now over here is a small graph which you probably can't see, and it shows the density. Well, basically it's a curve of planets in space where they are in our solar system and how dense elements are. And there's one model of solar system formation that you have denser elements close toward the sun and lighter ones further away, which kind of bears out when you look at it. Right? And if that theory holds, Mercury will be super dense, which means lots of heavy metals. Right? And I'm not saying we go to Mercury to get uranium to shred. I'm saying we go to near-Earth objects and asteroids that are in Earth's orbit or deeper in, or closer into the sun, for the uranium. Not because we need that much uranium, we could use thorium, we have plenty of it here, but because this is ridiculously unsafe and we simply should not be doing this on Earth. Right? Because you can generate mountains of waste, and we have enough trouble with the waste we have. Right? So we should go to space and find a near-Earth asteroid and set up a factory there. Right? That's ridiculously expensive, right? But it could give you $1 grand a day, and it's safer. It's worth the extra trouble and the money. I think we should pay it. If you're having a space race, I'll get up and say, Mr. President, go pay it. Don't complain. That's a good deal. Now, there'll be other technologies you want to work on as well to make this project work. One's cryopreservation. There are proteins that certain frogs have in their systems that allow them to freeze, literally freeze. And then when it gets warmer, normally, when spring comes around, they thaw out and they go back to being frogs. They never know what happened to them. Right? This stuff is the holy grail. If we can put that in people, we can travel. And suddenly life support is not an issue. You turn it on, turn it off. You turn your people on, you turn your people off. That's fantastic. Right? So we got to work on that. I think we need to work on artificial intelligence. If you're setting up your probes and landers, someone recently on this high-tech page said, okay, if we send a probe to Enceladus, the delay on sending a probe over, or to Ganymede, it's pretty significant. So how are we going to send a rover what to do? Well, we can't. We can't steer a rover with a joystick that way. You should be able to give it basic instructions for like what we'd like it to do, and it should be able to figure out what it's doing on its own. If you're sending a probe to Alpha Centauri, it's going to take you 4.5 years, just about almost 4.5 years, to hear back that it saw there's something in the way. Like, okay, there's a giant iguana spitting fire. What do I do? There's no point replying, is there? Right? There's no point, because the storm would have washed it away by the time it got there, assuming the iguana didn't eat it. So it has to be able to know what it's doing and say, okay, probe is logged. The iguana was nice. We had tea. I've cut a deal with them. It's a good deal. We're giving them all, all our small children of this age, whatever. But we have to be able to make decisions, right? It's radiation shielding. Space is a very unsafe place. There are models now for using electromagnets to try and protect space travelers from radiation and charged particles. It's not going to work for stars that don't have charge, right? And we're going to have this thing producing gamma rays anyway, out the back, without any charge, and they're going to go somewhere. So we have to work on shielding issues. And also I think we're going to develop von Neumann technology. You're going to be talking about this all the time, because I'm really fond of this stuff. Now let's talk about von Neumann, John von Neumann. He was a British scientist, mathematician, and he sat down and said, okay, well, we want factories to make safety pins. Factories to make safety pins. Why don't we have factories that make factories that make factories? And then we have all the safety pins we'll ever want. Right? There's a picture from XKCD. Life taunts engineers every day with this problem. And we're surrounded by von Neumann machines. Everything living can make copies of itself. And with a bit of help, but basically yes. Right? Life just happens, and life is powered by the sun. So we are surrounded by examples of cheap, reproducible technology that is powered by unlimited energy and can consume all the resources you put in front of it and make more of itself. And then make safety pins. Right? We're living proof of this ourselves. Right? So we know it can be done, and we really ought to get it done. And I think it is key to solving not just the problems of a manned mission or an unmanned mission, but just also to get to the problem that we're facing in the 21st century. Like Liyanage talked about in her presentation about the challenges of construction and maintenance for making sure we don't lose our cities and people aren't displaced in huge amounts. You know what's cheaper than billions of dollars, or what was it, trillions of dollars in some cases, to protect a town? One robot. Let's spend all the money, make one robot that's fast and smart enough to make another robot. Then they'll make a few more, and they'll make a few more, and they'll make a few more, and then they'll start fixing dikes. And maybe the dikes will start making more dikes. Right? If you want to get caught, and then we can actually do the repairing the environment, right? We need to scrub the carbon now. We need to make coral reefs full of carbon and sequester them deep underground. All the things we can do, right? And von Neumann technology is a key to that. And I think one way or the other we're going to have to develop it. If the space race means we get off our butts and do it sooner, that's a win. So now we get to the actual mission, the Alpha Centauri mission. We talked about the technologies that happen, and now we're going to talk about details, right? So, assuming the race starts in 2018 when the James Webb Telescope says, oh look, there's life in Alpha Centauri, the latest a ship can launch, if we want to put people on Alpha Centauri by 2100, the latest you can launch is 2057. Like, it's just 39 years from when James Webb finds life to launch date. 39 years. So you're sitting there, you know, your congressmen, your senators, you're a bunch of NASA scientists, and your president, and you're going, we have 39 years to send people to Alpha Centauri to get them going, right? And we're not going to live to see what happens. Well, maybe we will, didn't happen, right? So again, I think that will have to be driven an Apollo level challenge. And I think if China gets in, China's into the America will have to respond. Right? Nobody wants to spend money on a space race. It's an incredibly expensive process. It has dubious benefits in some cases. Maybe you're better to let the economy expand. These things happening anyway. It costs money. So you need to feel a threat, and the threat has to be more than, you know, oh well, if we don't study this.